Welcome everyone to this first keynote of already the last day of EuroBioC 2020. And on behalf of the organizers, I hope you're enjoying the conference. And I would just like to take this opportunity to mention that a few of us will meet at the tables in the lounge after the conference this evening for an informal post-conference chat. And you're all, of course, very welcome to join us if you would like. So with that, it's a great pleasure for me to introduce our keynote speaker, Luke Zappia. So Luke is a postdoc in the lab of Fabian Theis at the Helmholtz-Zentrum Munich Institute of Computational Biology and the Technical University of Munich. And before that, he did his PhD with Alicia Oschlag in Melbourne. And Luke is well known for his many contributions in the single-cell field, for example, the splatter package, the clustery package, and the single-cell RNA tools database, which is a really nice resource. And today we will hear about recent work on interoperability between Bioconductor and Python, especially for single-cell RNA-seq analysis. And before we get really started, just another reminder to please add all your questions in the Q&A tab and upvote other questions that you're interested in, and we'll take the Q&A after the talk. So with that, we're very much looking forward to your talk, and the screen is yours, Luke.
Cool. Thanks, Charlotte, and thanks for the organizers for inviting me. It's been a really great conference, and obviously it would have been nice to see everyone in person, but we can't do that. So today I'm going to talk to you about interoperability, but I also want to start by defining what I kind of mean by that, because it could mean lots of different things in different contexts. So for me, it's the ability to quickly and easily switch between languages or platforms as required during an analysis. And this could be any language or platform, but I'm going to focus on R and Python because that's probably what's most relevant to most people. So why do we actually want to do this? There are a few reasons I think are really important. One is to take advantage of the strengths of different languages, just because of the way they work. Some languages are better at some different things. So for example, a lot of the machine learning stuff is heavily based in Python, and it's easier to use there. While R is good at kind of statistics and visualization and that kind of thing. The second one is to make use of packages that exist. I'm sure a lot of people have had the situation where they've read a paper, thought that method looks kind of interesting, thought maybe they'll check out the software, and then it's not in R or whatever language you use, and you go, maybe that's a bit hard, I won't bother. If we make it easier to move between languages, that's less of a problem. And the third one is to avoid unnecessary re-implementation of methods. And I don't mean things like PCA, which are obviously useful for any language and is a really general thing. I'm thinking more about specific methods that someone's put a lot of work into implementing, and then someone else goes, that's not my favorite language, maybe I'll re-implement it. And now you've got two versions of a package. They both need to be maintained over time, inevitably what happens is one gets updates and the other doesn't. Maybe one gets kind of deprecated, and it causes a bit of confusion in the community and doubles the amount of work people have to do in terms of maintenance. So that's kind of what I'm talking about. And I'll focus mostly on R and Python, like I said, and Bioconductor. Before I get onto single cell, which will be my kind of example, I want to take a look back and look at what the bulk analysis landscape looks like, because that's probably what was lots of people's introduction to Bioconductor and bioinformatics. That was definitely mine. So in the bulk world, there are kind of three main packages that people use: DSeq2, EdgeR, and Limr. There are lots of others, obviously, but if someone comes to you and says, hey, I want to analyze some RNA-seq data, I've never done it before, maybe I'm a biologist and I've never really programmed before, you're probably going to point them to a tutorial for one of these. They're all really well maintained. They have lots of good documentation and lots of use. They're not necessarily super compatible with each other. They all use different objects, for example, but they're all available from Bioconductor and they all use R. So lots of people are drawn into the same community, and that leads them to participating and joining into conferences like this. If we look at the single cell world, it's a fair bit different. there are still three main packages. Bioconductor based around the single cell experiment object, the SARA package, which is also in R, but it's available from CRAN. And in the Python world, we have scanpy, and the ANDATA object is an object it uses. So again, three packages, but instead of being in one community, we have three different repositories and two different programming languages. And that inherently just makes it a bit more difficult to meet between each of these and take advantage of their strengths. And what happens is that most people end up using one of them and sticking to that ecosystem. I don't have a lot of evidence for this, but I would suggest that if your lab is a bioconductor lab, you'll use the bioconductor packages. If your lab's a Python lab, you'll use the scanpy packages. And I think most other people will probably start with SARA, which I think has the biggest user base, although I don't have a lot of evidence for that. What I do have some more evidence for is what developers do. So we can look at the tools in the single cell RNA tools website, which, as Charlotte mentioned, is a database that I maintain, cataloging tools for analyzing single cell RNA-seq data. And there are about 800 tools in there at the moment. Of those, about 60% use R, about a bit less than 40% use Python. You can use more than one platform per tool, so there's a little bit of overlap between those. Of the R tools, about 10% are available from CRAN, and about 16% of those depend on the SARA package, which is actually only 7 packages, and I was quite surprised that it wasn't higher than that. In the bioconductor world, about 24% of the packages are available from Bioconductor, and of those, 70% depend on the single cell experiment object. So I think this is a real strength of Bioconductor and shows the work that people have put into developing this infrastructure and encouraging people to use it. On the other hand, in the Python world, about 40% of the Python packages are available from PyPy, which is kind of the equivalent of CRAN, although I think it's important to note that it's much easier to get a package into PyPy than it is into CRAN. You don't have to go through the same process of getting it approved and proving that all the tests run, etc. And of those, about 25% depend on the ANDATA object package. So this isn't complete. I know there's some stuff that's missing, and I'm not showing you what all the tools that are only available from GitHub, for example, depend on. That information is just a bit harder to get. But we can see a little bit where developers are working. So there's a lot of packages that are available from Bioconductor, which is part of the reason we're all here. But I'm not sure that necessarily correlates with what users are actually using. Cool. All right, so the question now is, how do we actually make it easier to move between different languages? This is particularly relevant to me because I did my PhD in a lab that is based around Bioconductor, and that's where my packages are. But I'm now working in a lab that is heavily Python based and is the developer of scanpy. So luckily the infrastructure for this mostly exists, and I'm going to take you through it one at a time, starting from the really low level direct interface to Python through to packages for specific single cell RNA-seq analysis. Just before I get to those, a quick disclaimer that most of this isn't my work. It's work by other people in the community that I want to highlight because I think it's really interesting and useful, but I'm not trying to claim it as my own. So I'll try to attribute people as much as possible with their GitHub details, etc. The other thing I want to point out is this isn't only something that people in the R world are interested in. People in the Python world are also interested in using R. And in some ways, they're actually more interested because of how much stuff exists in Bioconductor. So I'll also point out where there's kind of Python alternatives that do the same thing in the other direction, if you're more of a Python person. So the first package I want to talk about is Reticulate. which is maintained from people from our studio. This is the basic interface between R and Python. It's equivalent to the rpy2 package if you're in the Python world. Honestly, I don't know a lot of detail about how this works in the background and what makes it possible, but I can show you how you use it as a user or developer. So this is a really short example of using Reticulate in a normal R session or script. You load the library, you tell it what Python environment you want to use, either by giving it a path to a Python executable or telling it which virtual environment or conda environment you want to use. And once you've done that, you can import a Python library just like you would in a Python script using this import function and save it to a variable. And then you can access functions within this library by using the $$ operator in R in the same place you would usually use a dot in a Python script. So here I'm using the data frame function in the pandas package, and I'm passing it as arguments an R data structure. So it's a list that contains normal R vectors. And what Reticulate will do is convert this R object into the equivalent Python object, pass that to the Python function, get back a Python object as a result, and then convert that back to an equivalent R object. So I'm passing in an R object here, and what prints out looks like a normal R data frame, even though it was created in Python. We can also do this conversion explicitly. So we create an R object like this vector and pass it to the R to Python function, and we'll get back the equivalent Python object, which is a list. Or we can do that in reverse using the Py to R function. So this is using Reticulate in a script. What I think is really cool is if you use it in an R Markdown document. So hopefully most people are familiar with what this looks like. We have chunks of code which are separated by backticks like at the top. And usually those are R chunks, so they run R code and print out the results. But we can also create Python chunks just by replacing the R with Python, where we can write native Python code. It will be run in the same way by Reticulate and R Markdown. And it has the same kind of consistent environment like we do with R chunks. So if I create a variable at the start of my document, I can use it further down. It's maintained throughout the document. So we have both these two environments, R and Python, and we can convert between objects between the two by using these special variables. So in our R session, we have a Py variable, and we can access Python variables inside that using the $$ operator. Or in our Python session, we can access R variables using this special R variable, and then the $. Operator access specific things. So I think this is really cool if you're already comfortable using Python a little bit and setting up your Python environment. This lets you write native Python code, so you can do things like copy code directly from a tutorial. You can still convert between them when you need to, but you don't have to worry about converting the syntax to Reticulate syntax every time you want to do something. You might be interested in what things actually get converted between Python and R. So basically Reticulate will take care of most of the common objects that we use. So vectors in R return to Python lists, lists in R return to Python dictionaries, matrices return to NumPy arrays, R data frames return to pandas data frames. If you use something that's not on this list, basically what you get back is a reference to a Python object. So it will print out like it does in Python, and you can still access things inside that object, but you can't quite interact it in the way you would with a normal R object. So Reticulate is super great. It gives us a really nice interface to Python, but there are a few limitations. One is that you have to manage your own Python environment. So that can be really intimidating for people new to programming, particularly say a biologist who has learned to do some analysis in RStudio. Having to go to the command line to install packages is maybe a bit intimidating. You still need to have some familiarity with Python. You need to, for example, know how to access functions which might be in a sub-module of some package. And the conversion only supports common data structures by default, although you can write extensions for particular things. So to address some of those, Aaron Lund has developed the Bacillus package. And what this does is manage the Python environment for you. So from the point of view of the developer, you specify a Python environment you want to use, you give it a name and link it to a package, and then specify the Python dependencies you need for this package. You then write a function that uses those libraries by Reticulate, and then you wrap the function in the environment using the Bacillus run function. So you say, here's my environment, I want you to run this function in that environment. From the user's point of view, they load your R package like normal. They run what looks like an R function. In the background, Bacillus takes care of creating the Python environment. So this happens the first time that's used or when the package is updated. It then runs your Reticulate code in that environment, returns some output. So to the user, it looks like you've provided R objects as the input and got an R object back with a normal R function. But in the backend, this is all happening in Python managed by Bacillus. So that has a few advantages over straight Reticulate code. It doesn't require the user to know anything about Python or how to set up and manage an environment. And the other thing I think is really important is that it allows you to have different environments for different R packages, which can often be a challenge if you're managing one big Python environment for a package. Things have different dependencies that might clash. This way, everything's kind of encapsulated in one environment for each package, and you don't have to worry about clashes so much. So that's kind of the core general Python infrastructure. I'm going to talk to you now about a couple of packages for single cell specific analysis. The first one is CellConverter, which I developed with help from Aaron. This is basically an interface that lets you convert between single cell experiment objects used by Bioconductor and data objects used in the Python world. The Python equivalent is the data to RI package. So the way this works is we might have a .h5add file, which is a file used to write an data object to disk. It's a HEF5 format. We can use CellConverter's read h5add function to read that in. It will use the data Python package to do that, gets back a Python data object, and then converts that to a single cell experiment object, which it gives back to the user. You can then use that for whatever analysis you want to do, or maybe you've started in R and you want to take your analysis to Python, and you can do this in reverse using the write h5add function, which will convert your single cell experiment to a Python data object and then write that to disk. This all happens within a Bacillus environment, so again, you don't have to worry about dependencies. But if you are comfortable managing your own Python environment, or say you're working in an R Markdown document, you can access the data.sce and the sce to data objects directly. You just need to make sure that you have data available. For single cell people, you might be interested in exactly what's converted. Most things go in both directions. So for example, assays in the single cell experiment are converted to the X matrix and layers in an data object. The important thing here is that things transposed, so the rows or columns are the other way around. Col data is converted to the ob slot in your data. Row data is converted to the vars slot. Reduced dims, which is things like your PCA and UMAP embeddings, are converted to obs m in an data. There are a few other things that aren't converted. One is var m in the data object, which is kind of equivalent to reduced dims, but on features rather than cells. So we can move that into a single cell experiment in R, but we can't convert it backwards at the moment. And the other one is things in metadata or the unslot in your data. Both of these are unstructured lists that could have any type of object in them, and might not have an equivalent in the other language. So basically, try to convert these if we can. If we can't, we give you a warning and say what wasn't converted. This isn't the first package to do conversion between objects. scRNA, for example, has lots of conversion functions, particularly going to and from a scRNA object, but you can also use that to go to a single cell experiment. There are a couple of others I'll point out. One is scEasy, which is available from GitHub. This again does conversion between several formats, including ANDATA, scRNA, Loom files. So it's a bit more flexible than CellConverter, but it is only available from GitHub, so you can't depend on it in your own Bioconductor package, for example. And it doesn't use Bacillus, so you have to manage your own environment. The other one is ANDATA, which is available recently from CRAN. This also has functions for, say, reading in a .h5add file, but instead of getting back a single cell experiment, you'll get back an R ANDATA object. So equivalent of the Python object, but written in R. It'd be interesting to see if this is taken up by the community and used at all, and there might be some synergy there with CellConverter, but for the moment, that's just another option. So that's converting between one format and another, but you still need to be able to use Python at some stage if you're doing things this way. The other option is to write a package which directly wraps a Python package for doing analysis and using that from R. So as an example, here's the velociraptor package written by Kevin, Aaron, and Charlotte. And this wraps the Python scvelo package. Here is how it works from the point of view of a user. You have a single cell experiment. You give it to the scvelo function in velociraptor. It will extract the information it needs, mostly the expression matrices for your splice and unspliced counts, convert those to a Python ANDATA object, run them through the functions in the scvelo workflow, get the final Python ANDATA object, and convert that to a single cell experiment using CellConverter. So from the point of view of a user, you've put in a single cell experiment and you've got back a single cell experiment, but in between, all this actual analysis is happening in Python. You might be wondering what scvelo actually does. So I want to talk to you a bit about those and a couple of other methods from the TICE lab. So scvelo was written by Volker Bergen, who's a PhD student, and it builds on this idea of RNA velocity, which became popular a couple of years ago. So the idea here is when we think about gene expression, we usually think about it being mature mRNA molecules, but we also capture some immature, unspliced RNA in the process, which still contains introns. And by looking at the ratio between these two, we can infer something about the regulation of the gene. So this is what's showing in the plot in the middle at the top. For a single gene, let's assume it's turned off to start with. First it's induced or upregulated, and we see splice counts go up, unspliced counts go up, followed by splice counts. And then there's some kind of steady state where things are being produced at the same rate they're degraded. And then for whatever reason, that gene is down-regulated or repressed, and we see the process in reverse. Unspliced counts go down first, and then splice counts follow afterwards. If we plot these against each other, like in the plot underneath, here each point is a cell. The spliced counts are on the x-axis, and the unspliced counts are on the y-axis. We get this nice kind of almond shape where, again, we see the spliced reads increase first. The unspliced reads increase first, followed by the spliced reads, and then there's some kind of steady state where things aren't changing so much, and then the process is reversed. And if we look at the difference from this kind of steady state fit for each cell, we can infer a velocity for this particular gene. And if we do that for every gene, we can get a overall velocity for the cell. As great as this is, there's a couple of problems with this steady state model. And one of those is that if the induction phase and the repression phase work on very different timescales, then this fit will not quite be right. And this is the problem Volker tried to address in the work he's done in scvelo. So what he came up with is a dynamical model of RNA velocity, where he fits these three different parameters: the transcription rate, the splicing rate, and the degradation rate. And does this using a kind of maximum likelihood approach. And once we have estimates of each of these three parameters, we should have a better idea of what the real steady state is, or whether that gene is in a steady state or not. And from that, we can get better estimates of velocity. So here's a quick example. On the left, we have the velocities from the original steady state model, and on the right, the dynamic velocities. And you can see that in general, the dynamic model is a little bit neater, maybe. There's a couple of things I'll point out in particular. These kind of greenish cells on the top left. In the steady state model, the arrows are a little bit unclear. They're kind of pointing off to the side, which doesn't quite make sense. And there's some going in the opposite direction. Whereas in the dynamical model, we kind of have this nice whirlpool or vortex. And if you look at those cells a bit more closely, you can find out that those are actually cells that are involved in the cell cycle. And that's what that kind of swirl is representing. There's also a couple of places like the purple epsilon cells where we get estimates from the dynamical model that we seem to be missing from the steady state model. The other thing that Volker infers in scvelo is this idea of a latent time. So on the left is output from a normal diffusion pseudotime analysis, where we have, starting from the left, cells going through to the right, and the two kind of endpoints on the right are assigned the same time because in this space they're kind of the same distance from the root cell. With the latent time we get from scvelo, we can actually differentiate between these two and see that the one in the middle is given a later time period. And if we look at more closely at those cells, we can see they're actually from a sample from a later time point. So again, the dynamic model is giving us a little bit more information. There are a few things it doesn't tell us, however. One of those is, what's the likely fate for each individual cell? Or the opposite question is, where does a particular population come from? We also can't tell what genes are, how gene regulation changes for cells that are headed towards a specific fate. So to answer those questions, Marius, who's another PhD student in Theis lab, developed a package called CellRank. Unfortunately, there's no R wrapper for this available yet, although I hope to make one. But you can use it by using the cell converter to save your data as a and data object and then do the analysis in Python. So the intuition between CellRank is pretty straightforward. We have our multi-dimensional space where we have a velocity for each individual cell. What CellRank does is look at the neighbors of each cell and the velocity for that specific cell and calculate a probability that this particular cell I will turn into each of its neighbors. So here we have the velocities heading towards the top right, so we end up with higher probabilities for the right cell and the top cell than we do for the other two. We can do this for every cell, and then we can combine the results and do a little bit of fancy maths to define these macro states. So these are important states in our network, and they can be the terminal states, so fates that cells are headed towards to, an initial root state, and sometimes we also identify these metastable intermediate states where expression doesn't change for some reason. Perhaps it's waiting for a stimulus of some kind. Combining these with our individual transition probabilities, we can get a fate probability for each cell. So what's the probability that a particular cell anywhere in our data set is going to turn into cell type A or cell type B? We can also look at individual genes for each of these fates. So looking at the top gene in the middle here, it's highly expressed in cells that are heading towards fate A, and less expressed in those heading towards fate B, or the opposite way around. We can also order these genes. So if we're looking towards a specific fate B here, what gene turns on when? So gene X turns on first, then gene Y, and then gene Z. Putting this all together into an example, because I know that was quite a lot to take. Here is an example of pancreas development. On the left, we have the metastates identified by CellRank, an initial state, various terminal states. We can look at a selection of cells and say what fate are those headed towards. We can also do things like condition on a particular gene. So here's NGN3 expressing cells, and they're more likely to turn into beta cells, which are the insulin expressing cells in the pancreas. We can then look at the genes that are important for different fates. So if we look at the beta fate, we see PDX1 is expressed in quite a few of the different lineages, but is more highly expressed in cells that turn into beta cells and later on in the process. In contrast to, say, LRS4 or IRS4, which is expressed at about the same time for cells heading towards each of the fates, but much more highly expressed in those that are going to become epsilon cells. All right, that was a whirlwind tour of CellRank for you. So just to quickly sum up everything I've talked about today, interoperability between Python and Bioconductor is already possible. It just takes a little bit of work from us as developers to make it easier for users. Cell converter is one kind of example, which will let you convert between single cell experiment and data objects and move your data between R and Python as you need to. And if you're doing an analysis of some kind of dynamic process, I strongly recommend taking a look at scvelo and CellRank. And hopefully they'll provide you with a little more information. So quickly thank people, mostly all the developers of all the packages that I've shown today, plus everything else that we use all the time. It's really a great contribution to the community. Marius and Volker shared me some of their slides so I could talk about their work. And thank you all for listening. I'm happy to answer any questions.
Thanks so much, Luke. That was great. We already have a bunch of questions, so to everyone else, please keep them coming. So the most upvoted question is from Davide, who is saying, thanks for the great cell converter package. Since undata is stored in HDF5 format, would it be possible to read and write it directly in R with RHDF5 or HDF5 array? And does cell converter leverage this when user has an HDF5 backed single cell experiment?
I guess it would be possible to do it directly, but I guess what I kind of talked about at the start was trying to avoid doing that as much as possible, because there are things like recently there was a big change in the Android object and where they stored a couple of things. If I had re-implemented that, I'd have to update things. All I need to do now, if something like that happens again, is change the version of Android I depend on, which is easier. With regards to the backing, there are options to access backed HDF5, Dr. H5 add files in Cell Converter. I did mention that kind of this conversion works, but it hasn't been super extensively tested. So there are things like that which work in theory, and we've tested on many things, but we really need people in the community to tell us if things don't work so that we can update and fix them, because we just can't test every possible thing people might have in their objects.
Yeah. If I may just add a small question to that, what about delayed arrays? Would that how would that be handled? Will that be smoothly working?
I think it should. I'll be honest that Aaron took care of most of that side of things because he obviously has more experience with the file back stuff. I think it should work, but you would have to test and see.
Great. So the next upvoted question is from Friederike, who's wondering, are there any reasons not to use these awesome conversion packages? Like, are there instances where performance might suffer or the like? And what are the worst bottlenecks in your experience?
Yeah, so I guess there are some reasons. For Zell Converter, like I said, it's not been super extensively tested. So there are probably some situations where you will end up with, say, duplicating information, which might be an issue if you have particularly large data sets. And that's obviously something we would like to improve as we go along. And yeah, I guess there's kind of bottlenecks around. It's still a bit of a pain to kind of have to write things to file and then go read them in somewhere else. But that's kind of the most generalized way to do things, which is why what we started with. So it's definitely not perfect, but I think particularly for people who aren't super confident or experienced programmers, try to make it just a little bit easier.
Yeah. Right. So then there is a question more on the velocity itself. So wondering, Chiro was wondering how this velocity algorithms perform in integrated datasets or datasets composed of several batches.
Yeah, so that's definitely a known problem. At the moment, there's not really a good way to work, or we're not sure what the best way to work on an integrated dataset is. So you can obviously run it on each sample individually. But that's something that Volker's definitely working on, is how to kind of do an integration for velocity inference. But yeah, it's a known unsolved problem for the moment.
Yeah. Okay, so we have another question from Davide, who's wondering if it would be feasible or useful to wrap SCMPy itself in a bioconductor package.
So you could definitely do it, but I'm not sure there's much reason to. SCMPy basically implements the standard kind of analysis that we do and is available in several places. It's very similar to what Sera does. It's very similar to what some of the core bioconductor packages do. So I'm not sure you would gain a lot from doing that. I guess in theory, SCMPy is more scalable because it's Python based, but running it from R, I think you would end up losing that because you'd have to transfer stuff anyway. So you could do it, but I'm not super sure whether there's a good reason to.
And I guess a kind of follow-up question to that is how do you think the field will go forward? Do you think it will change somehow, given that we have all these interaction abilities now? Will there be less packages in the future, or will there be something is implemented really either in Python and R, or R, and then there will be this interoperability used?
That's a good question. I would kind of hope there would be less packages, not less packages, but more diverse packages. We have a lot of packages that do the same thing or do very similar things. And I guess that's something I've tried to address a little bit with scRNA tools, is to try and help people available what already exists, so you don't go out and redo something that already is available. I don't think we're going to have people converge on one language, and if anything, I think we're more likely to have people split into different languages. And that's another reason I think that being able to move between them is important, so that we don't have these kind of siloed communities where bioconductor people don't know or use about the Python stuff and the Python people don't use the R stuff.
Yeah. Cool, so we have a few more minutes. So Federico has a question wondering whether older or newer versions of undata objects are supported in Cell Converter, or alternatively something like update objects, but for the undata objects.
Not really. So basically, we have a single ANDATA version as a dependency, which will probably get updated with each Bioconductor release. I think that's something that kind of fits in well with the Bioconductor release schedule. I would say that the ANDATA package is probably fairly backwards compatible. So I know there's definitely cases where you try and read an ANDATA object in Python or R, and it will do it, and it will give you back the result, and it will just give you a message complaining, hey, this object's old, things are in the wrong spot. So I think a lot of that backwards compatibility is taken care of in the Python side.
Yeah. Okay, so there's a question about CellRank from Friederike, who's wondering, do you know if CellRank has been applied to trickier data sets, such as from immune cells? If yes, how did it perform?
There are definitely some other examples in the CellRank paper. I'm not sure exactly what they are, or preprint on bioRxiv. I do know that for some reason, immune cells, or at least blood cells, are particularly difficult in terms of estimating velocities. So I'm not sure how CellRank would work on those. Something I didn't mention, which because it didn't quite fit with other things, but you can actually run CellRank on other information other than velocities. So there are examples of doing that in the documentation.
Great. So this was very informative. I think there are no more questions in the chat, so I think we'll round up here. And thanks a lot again for a great talk.